For many years, people have known about atoms from theory and from chemistry, from physics, from all the observations that I described in the past many videos about hydrogen atoms, the emission line spectrum, and all the calculations, and so on and so on. Now, but no one has actually seen an atom or atoms with their own eyes. No one. Until 1981, when Gerd Binnig and Heinrich Rohrer invented what is now called the scanning tunneling microscope. Let's have a quick look at how this microscope works. Now, suppose that this picture here shows the surface of, say, a piece of metal, and suppose that, well, maybe I'll just call it copper. Copper metal surface, where we have these rows of atoms arranged nicely on the surface. And suppose that I have a very sharp tip, a very sharp needle, like maybe a bit closer. This is a very sharp needle, maybe made of say tungsten, something very hard. Now, so this is the tip of a very sharp needle, and it's very close to the copper surface. Right. The way this works is by having a voltage between these two. So we might imagine, say, some kind of a battery connected between them. Okay, and as a result, this battery would try to cause a current to flow, but the current cannot flow because there's a gap here. Now this gap, as well, it's a bit like the potential barrier that I described when I talked about quantum tunneling in an earlier video. I'll describe it in a bit more detail afterwards. So anyway, the gap in between is a barrier. Okay, it's where the potential energy is higher than inside the atoms. Inside the atom, you know that the potential energies are negative. In the vacuum, here, potential energy is 0. So there's a higher potential in the vacuum than inside the atoms where the electrons are. So it is a kind of a barrier, like the vacuum becomes a wall, right? A potential barrier or potential wall that prevents electrons from just flowing from there to there. Okay, the electrons are blocked by the vacuum. But we understand from the earlier video on quantum tunneling that it is possible for the wave function of the electrons, say on one side of the barrier, to spread through the barrier. Okay, and if that wave function spreads and reaches over to, say, the copper surface, then it means that there would be a non-zero chance of finding an electron from this side of the barrier on the other side. And if that really happens, and it really can, then the electron can just hop from there to there and flow around the circuit. We call this a tunneling current. Okay, so in this way, electrons can tunnel through the barrier. So I'll explain a bit more about how, describe a bit more about this tunneling afterwards. But for now, let's just assume that the tunneling can happen, and let's see how this effect is being used, how this quantum tunneling is being used to actually get a picture of the atoms. Right, the way it works is this. This needle is sort of shifted sideways so that it moves parallel to the surface. Now, as it moves, the distance between the tip of the needle and the surface of the metal, you can see that the distance would keep changing, because if it is over a bump, if this tip is directly over an atom, the distance will be shorter. But if it is over the gap between two atoms, the distance would increase. So if the distance is smaller, there would be more current flowing through. There would be more chance for the electron to jump across. If the distance is bigger, the electron would have a smaller chance of jumping through. Okay, so this means that as this needle is moved sideways, and the distance keep changing, so the current actually flowing through would keep changing. Now, the idea is to have a meter to measure this current and record it onto the computer automatically, so that the computer can plot a graph of, let's say, the currents going through, the currents I going through against X. Now, if it does this, let's imagine what the results would look like. If it does this, we would, let me draw the graph here. So X, same as the X there, the current. We would imagine that the current would go up and down. Current would go up and down. So this current would depend on the spacing between here. So when the spacing is bigger, we get less current. When the spacing is smaller, we get more current. And the current can be directly related to the spacing by a formula, which I'll talk about afterwards. So therefore, from the current, we can calculate the distance between tip and the surface. So if you plot a tip, so then we can get a graph of the distance from tip to surface against the position X. And once we have a graph like this, it would be basically a picture of say a cross section of this atom, alright, along a certain line. Now, if we then shift the needle a bit and do it again along a different line, we could start drawing lots of graphs like this, alright, over different lines on the surface. Now let's try and imagine what we would get if we do that. Okay, so if we let's say if I have a line along the surface and I plot a graph like that, we get a graph that looks like this. If I then shift this sideways a little bit and do it again along a slightly different line, I might get another graph that looks like this. And then if I shift it sideways some more, it might look like this. And then go up again. And so on. So I might, if I put all of these graphs together onto one image, then we can actually see where the humps are for the atoms. Right? In this way, it is possible to actually get a picture of the whole surface, showing all the atoms, and that's how the scanning tunneling microscope is actually able to give us images of atoms on the surface.